Okay, welcome to physical chemistry. This is chapter N, the reshoot, because we decided to go ahead and do the part about electrolytes too. So here we are in chapter 10.1. For now we're doing non-electrolytes. Now we know that the chemical potential of substance I in an ideal solution is just equal to the chemical potential of substance I in the standard state plus the gas constant times temperature times the natural log of the mole fraction of the substance in the solution. Remember, we're abbreviating ID for an ideal solution, and the naught means standard state. Now we're going to just take the same equation and we're going to solve for the mole fraction of substance I. So we get mole fraction of substance I is going to be equal to E, the natural number, to the chemical potential of the substance I ideal minus chemical potential of the substance I in the standard state, divided by R times the temperature. And this, of course, has to be absolute temperature, kelvins. And this is only for non-electrolytes, and we're talking about ideal or ideally dilute solutions for now. But what we want to do is we're going to define the activity of a substance I as just lowercase a sub I. We're going to call that the activity. We're going to define it as E to the mu I not ideal, the actual, minus mu I naught divided by RT. So this is going to be for a real solution. Then we're going to solve for this chemical potential, the real chemical potential here. So here's an intermediate step. We just take the natural log of both sides. So we get the natural log of the activity of substance I is just equal to the chemical potential of the substance I minus the chemical potential of the substance I in the pure state, or standard state, divided by RT. And then of course just take E to both sides, get rid, and no. How do we do that? Oh, never mind, we're solving for mu I. So then we can just get mu I, it's the chemical potential of substance I, is equal to the chemical potential of substance I in the standard state, plus R times the temperature times the natural log of the activity. So notice how it looks similar to this, but instead of just mole fraction, we have activity, which will give us a difference. Continuing on physical chemistry, chapter 10.1, we're still talking about solutions of non-electrolytes only. So we showed before how mu I, for real, not ideal, is equal to mu I naught plus RT natural log of the activity of a substance. So this would be true for any solution, not just ideal. So where we had the mole fraction before, we have the activity. So the activity of substance I replace the mole fraction of substance I. Now, if you have an ideal or an ideally dilute solution, then the activity of I is equal to the mole fraction of I. Also, when the chemical potential of I is equal to the chemical potential of I in the standard state, well, that means you're in the standard state. So AI is equal to AI naught, and that equals to 1, because the activity is going to be 1 in the standard state. Now, that gives us then, if you put in natural log of 1, you get 0. So this whole term here, RT natural log of the activity of 1, will give us 0. So that just means that the chemical potential is the same as in the standard state. Now, we can take those two differences and subtract them. The mu I, the chemical potential of I, minus the chemical potential of I ideal, and that will give us the RT natural log of the activity minus RT natural log of the mole fraction. Now, using the rules of logarithms or whatever, that's going to give us RT natural log of the activity divided by the mole fraction. So this ratio here, the activity divided by the mole fraction, we're calling this our departure from ideal behavior. Now we're going to define gamma to be that ratio. So the gamma of substance I is equal to the activity of substance I divided by the mole fraction of substance I. So this is your lowercase gamma, and this is the activity coefficient. A is the activity, and then of course chi, or x, is the mole fraction. Now, if the gamma of I, or the activity coefficient of I, is equal to 1, oh no, then that's for non-electrolytes only. And this isn't an ideal or ideally dilute solution. Obviously, then if it's a real solution, it'll be something else. Now, the activity of I, it always has to be greater than 0, and the gamma of I, it also has to be greater than 0. And both of them have no units, which would be kind of obvious because you can't take the natural log of something that has units anyway. Physical chemistry, we're wrapping up chapter 10, section 1. So we showed what AI means. We defined it on the previous slide. And the reason we found it is because it's a measure, the activity of I is the measure of the chemical potential, mu-I, in the solution. Because they're proportional to each other. So if your chemical potential of substance I is increasing, then the activity of substance I is increasing. This is Physical Chemistry, Chapter 10. We're starting Section 6 now. We're going to be talking about solutions of electrolytes. And there are actually two different types of electrolytes that we'll be talking about. One is a true electrolyte, which is something that exists in ions as a pure state instead of molecules. For example, sodium chloride, potassium iodide, lithium fluoride. These are not technically molecules. There's no such thing as a sodium chloride molecule. It's all one big ionic lattice. On the other hand, there's potential electrolytes. Now, these are substances that exist as uncharged molecules in pure state. For example, this I think is acetic acid. It's a neutral molecule, but you dissolve it in water, then it makes ions dissociate. Same thing, HCl, hydrochloric acid. It exists as a molecular gas in the pure state, but when you dissolve it in water, it dissociates into ions. So those are potential electrolytes. Either way, we're going to write either type of electrolytes, potential or true electrolyte, in this format. You've got the metal and the non-metal. So capital M here we're using for metal, and the X we're using is non-metal. It's a mole fraction. So you put like HCl or Ki or whatever. And there's a subscript here. This is the lowercase nu. So you have a one for the plus and one for the minus. So the cation and the anion. And this is just your number subscript. Like for HCl, it's 1 and 1. Or I don't even have any different examples, do I? But we'll be showing this more later. Physical Chemistry, Chapter 10. We're continuing with Section 6. We're talking about electrolytes. We already talked about how there are two types of electrolytes, true electrolytes and potential electrolytes. And then we showed you how any kind of electrolyte, it'll be written as the metal and the mu plus, so that's the subscript, the number of each of these. And then X for the non-metal, and that's mu minus, and so that's the number of the anions. So if you take this solid and you dissolve it in water, then remember you'll get mu plus of the metal ions, and those are Z plus, and then you'll get mu minus of the non-metal ions. And those are Z minus, because this has a positive charge, this has a minus charge. And then of course nu plus and nu minus, there have to be integers, because those are the subscripts from your molecular formula. So as an example, let's say we have barium nitrate. So our metal here is barium, and then our non-metal is the whole nitrate ion. And notice we don't bother to show the superscripts here. And then nu plus from the barium, that's 1. And then nu minus from the nitrate, that's 2. And then the charge on the plus, the cation, that's 2, positive 2. You don't have to write the 2 plus or anything. And then Z minus, that's the charge on your anion. Each one, individually, that's going to be minus 1. So you don't have to write it just like 1 negative, like you might have to with a superscript. Now potential electrolytes, that's going to be the same thing. Let's say we have calcium, I guess this is phosphate. So our metal here is calcium. Non-metal here is the phosphate ion. So our nu plus, oops, did I screw something up here? I might be missing a 3 here. Yeah, I'm missing a 3 there, duh. Okay, so anyway, our nu plus is 3 obviously, and then our nu minus is 2 obviously. And then our Z plus, that's going to be 2 because the calcium ion is plus 2. And then our Z minus is minus 3 because the phosphate is going to be minus 3. Now if we have some sort of substance so that Z plus is 1 and the absolute value is Z minus equals 1, then we call that a 1-to-1 electrolyte. Now in our example, calcium phosphate, then we have 2 to 3. Notice that you have the 2 for the non-metal first and then the 3 for the metal second. Now for comparison, let's say we have calcium nitrate, which is similar. We're going to get calcium 2 plus ions and then 2 nitrate ions. But you notice these calcium ions and a nitrate ion, it can recombine, making this more complex ion here. Still got a +1. So this is what we call an ion pair. And the ion pairs form with a more and more concentrated solution. The more concentrated the solution, the more likely that ion pairs are going to form. This is Physical Chemistry, Chapter 10. We're continuing Section 6. We're talking about solutions of electrolytes. Now we're going to talk about chemical potentials in electrolyte solutions. Now let's say we have an electrolyte in the form we had before, Mx, where M is the metal, X is the non-metal. So it dissociates. We're going to get M cations with a Z plus charge and the non-metal anions with a Z minus charge. So that's going to give us Okay, this is Physical Chemistry, Chapter 10. We're continuing Section 6. We're learning about electrolyte solutions. Now we're going to talk about chemical potentials in electrolytes. Now, we showed how electrolytes, they have the form Mx, where M is the metal and X is the non-metal. So, for our metal cation, we're going to have a chemical potential mu plus. And then for our non-metal anion, we're going to have a chemical potential mu minus. And then if we form any ion pairs, in the form of metal, non-metal, etc., we're going to have a chemical potential of mu sub IP. So IP is abbreviation for ion pair. And then we're calling the solvent just A. So our chemical potential for the solvent is just mu sub A. Now we're going to, the chemical potential of just the cation would be the partial derivative of the Gibbs free energy with respect to the number of moles of the cation, holding temperature and pressure, and all other substances constant. So N is the number of moles, oops, this should be Ni is the number of moles of the electrolyte. And we want to hold everything else fixed. But just finding the chemical potential of the cation or ion separately is not really possible. So instead what we need to do is find the chemical potential of the entire electrolyte, I. So the chemical potential of our substance I is just going to be the same as we had before. The derivative of the Gibbs free energy with respect to the number of moles of the substance I, holding temperature and pressure, and the number of moles of the solvent constant. So right now we're just looking at one solution in a solvent. So mu here, this mu sub I, this is measurable. And I, of course, is our electrolyte, our solute. So hopefully you remember chapter 2, when we did the derivative of the Gibbs free energy, the exact differential is minus SDP plus VDP. So remember this is entropy, temperature, volume, pressure. And then plus the chemical potential of our solvent times the differential of the number of moles of the solvent, plus the chemical potential of the cation times the differential of the number of moles of the cation, plus the chemical potential of the anion times the differential of the number of moles of the anion, plus if we form ion pairs, then you have the chemical potential of the ion pair times the differential of the number of moles of the ion pairs. Now, what happens if we have no ion pairs then? Well, remember, electrolyte is still M nu plus and non-metal mu minus. So then the number of moles of the cations is just going to be equal to the nu coefficient of the cations times the number of moles of our solute. And likewise, the number of moles of our anions is just going to be the stoichiometric constant of I times, oops, that shouldn't be I. Should it? It should be minus times the number of moles of I. So the N minus, that's the number of moles of the anion, and N plus is the number of moles of the cation. Continuing on Physical Chemistry, Chapter 10, or in Section 6, we're talking about electrolyte solutions. So we just showed what happens if we don't have the electron pairs or ion pairs in a solution. Now what happens if ion pairs are formed? Well, we're going to have the number of moles of the cations, that's equal to the stoichiometric coefficient of the cations times the number of moles of the electrolyte minus the number of ion pairs. Likewise, the number of moles of the anions is going to be equal to the stoichiometric coefficient for the anions times the number of moles of the electrolyte minus the number of ion pairs. Now, if we put that in differential form then, we're going to have the differential of the number of cations is equal to the stoichiometric coefficient of the cations times the differential of the number of moles of the solute, the electrolyte, minus the differential of the number of moles of ion pairs. Likewise, the differential of the number of moles of the anions is going to be equal to the stoichiometric coefficient of the anions times the differential of the number of moles of the electrolyte minus the differential of the number of ion pairs. Now, let's say we substitute this into a previous equation. Oops. I used to know how to spell previous equation. Anyway, dG is equal to minus SdT. So remember, this is entropy, differential temperature, volume, differential pressure. Now we have the chemical potential of the solvent times the differential of the number of moles of the solvent. And then the chemical potential of the cation. And now we have the stoichiometric coefficient of the cation times the differential of the number of moles of the electrolyte minus the differential of the number of moles of the ion pairs, and then plus the chemical potential of the anion times the stoichiometric coefficient of the anion times the differential of the number of moles of the electrolyte minus the differential of the number of moles of ion pairs. Now, the chemical potential of the ion pairs, that's just going to be equal to the chemical potential of the cations plus the chemical potential of the anions. So, substituting that back in, we get the differential to Gibbs free energy is equal to minus the entropy times the differential of temperature, plus the volume times the differential of pressure, plus the chemical potential of our solvent times the differential of the number of moles of the solvent, plus the differential of the number of moles of our electrolyte, times the chemical potential, of our cation times the number of moles of our the stoichiometric coefficient of the cation, and then plus the chemical potential of the anion times the stoichiometric coefficient of the moles of ion, or cation. And then subtract out mu of, is this supposed to be, oh, that's plus. Okay, the chemical potential of the cations times the differential of the number of moles, or of ion pairs, minus chemical potential of the anions times the differential of the number of moles of ion pairs, plus the chemical potential of the cations times the differential of the number of moles of ion pairs, plus the chemical potential of the anions times the differential of the number of moles of ion pairs. Notice how these cancel out here at the bottom. So simplifying this, we get what we, just this top row here. The differential that gives free energy is going to be equal to minus the entropy times the differential of temperature, plus the volume times the differential of pressure, plus the chemical potential of our solvent times the differential of the number of moles of solvent, plus the differential of the number of moles of solute, that's our electrolyte, remember, and then all that times our chemical potential of the cation times the stoichiometric coefficient of the cation, plus chemical potential of the anion times the stoichiometric coefficient of the anion. Continuing on physical chemistry, chapter 10, we're in section 6, we're talking about electrolyte solutions still. So we showed before how the differential that gives free energy for adding a electrolyte solute into a solvent is equal to minus SDT plus VDP plus mu A DNA plus DNI times mu plus nu plus mu minus nu minus. I explained on the previous slide what that all means. Now we're going to do this at constant temperature and pressure, and obviously we're going to keep the number of moles of the solvent constant. So this term drops out from constant temperature, this term drops out from constant pressure, this term drops out from holding the electrolyte constant, so this is all we have left. So our differential that gives free energy for adding an electrolyte is just the differential of the number of moles of our electrolyte I times this whole term, the chemical potential of the cation times the stoichiometric ratio of the cation, plus the chemical potential of the anion times the stoichiometric ratio of the anion. So, also, since the chemical potential of our substance I is it just defined as the derivative of the Gibbs free energy with respect to the number of moles of I holding temperature and pressure and the number of moles of our solvent constant, then we know that the differential of the Gibbs free energy is just equal to the differential of the number of moles of our substance I times mu I. So, using these together, we can conclude then that the chemical potential of our electrolyte is just equal to the chemical potential of the cation times the stoichiometric ratio of the cation plus the chemical potential of the anion times the stoichiometric coefficient of the anion. This here is a very important equation. We're going to use this later on when we figure out how to calculate this stuff. So as an example, the boring one, of course, NaCl, sodium chloride. So if we want to know the chemical potential of the sodium chloride in an aqueous solution, it's just equal to the chemical potential of the Na plus ions in the aqueous solution plus the chemical potential of the chloride ions in the aqueous solution. Now, likewise, calcium chloride, same thing, except you got to pay attention to your stoichiometric coefficients here. Well, here's the subscript, but over here it becomes the stoichiometric coefficient. So our chemical potential of the calcium chloride in the aqueous solution is just equal to the chemical potential of calcium ions in the aqueous solution plus 2 times the chemical potential of chloride in an aqueous solution. So that's very important to pay attention to. Now, remember A, our standard is the solvent. The chemical potential of our solvent is just equal to the chemical potential of our substance star, which means pure, remember, at whatever temperature and pressure, plus RT, natural log of gamma XA times the mole fraction of A. This nomenclature means that it's the activity coefficient when we're using mole fraction as units. If we're going to be using a different type of concentration here, then we're going to be using a different gamma. So that's why we put this here, to show that this is gamma when you're using mole fraction. And of course A is for the solvent. Now remember, we said that the activity of I is equal to the activity coefficient of I times the mole fraction of I. Continuing on physical chemistry, chapter 10, we're in section 6 still. We're talking about electrolyte solutions. Now we were talking about how to find the chemical potential of substance when it is in a mole fraction form. But what we want to do is express it in terms of molality. So we're going to use lowercase m for molality, remember. So m plus would be the molality of our cation. Remember, that's in the form of metal Z plus. Do we write Z, M again? Okay, well, this probably should be an X here actually, but anyway. So we have M minus is equal to the molality of the anion. So that's our M of our Z minus. And likewise, our gammas are going to be different now, because now it's a molality scale activity coefficient instead of mole fraction activity coefficient. So we have gamma plus for the cations, and then gamma minus for the anions. So to find the chemical potential of the cations, it's going to be chemical potential of the cations in the standard state. Standard state meaning 1 mole per kilogram of solvent, not solution, don't get that twisted. And then plus RT, that's temperature obviously, times the natural log, our gamma plus activity coefficient times the molality of the cation divided by the molality of our standard state. Now remember, this gamma has no units, so these have to be in the same units. The units will cancel out, and then you can take the natural log, because you can't take the natural log of anything with units. And likewise for the anions. So if you want the chemical potential of the anions, you have the chemical potential of the anions in the standard state, plus R times the absolute temperature times the natural log, gamma the anions, the molality scale if you want to remember, times the molality of the anions divided by the molality of the standard state. Now, we're also going to talk about the limit of infinite dilution, is what this means. Gamma of the cation at infinite dilution, or gamma, this should be a minus obviously, gamma the anion at infinite dilution. Oh yeah, that's why I wrote it like that. The plus is here and the minus here. So at infinite dilution, that's where we say that their activity is equal to 1, because it's like an ideally dilute solution. And then remember what we had before. Chemical potential of our substance I is equal to the stoichiometric coefficient of the cations times the chemical potential of the cations plus the chemical potential of anions plus the chemical potential of the anions. I know I said that before, but we're going to use that again real quick. Continuing on physical chemistry, chapter 10, this is section 6. We're still talking about electrolyte solutions. So the chemical potential of the electrolyte we showed is equal to the stoichiometric ratio or a coefficient of the cations times the chemical potential of the cations plus the stoichiometric number of the anions times the chemical potential of the anions. So that gives us the chemical potential of the electrolyte is equal to the stoichiometric coefficient of the cations times the chemical potential of the cations in the standard state plus the stoichiometric coefficient of the cations times the gas constant times temperature times natural log of the molality activity coefficient times the molality divided by the standard state molality, and then plus, oops, this should be anions, the stoichiometric coefficient of the anions times the chemical potential of the anions in the standard state, plus the chemical potential of the anion, or the stoichiometric coefficient of the anions times RT times the natural log of the activity coefficient of the anions times the molality of the anions divided by standard state. We can combine all this, simplify it a bit. It looks scarier, but it's going to be useful. So we have the mu I, or chemical potential of our electrolyte, is equal to the stoichiometric coefficient of the cations times the chemical potential of the cations in the standard state, plus the stoichiometric coefficient of the anions times the chemical potential of the anions in the standard state, plus R times the temperature times the natural log. This is gamma of the cations to the coefficient, to the exponent, to this power of the coefficient of the cations. And then this is the gamma, our activity coefficient of the anions, and taken to this power with the gamma, or to the stoichiometric coefficients of the anions. And then we're also going to multiply it by the molality of the cations divided by the standard state, and then take that to the exponent to the stoichiometric coefficient of the cations. And then we're also going to take the molality of the anions divided by the standard state, and we're going to take that to the exponent to the stoichiometric coefficient of the anions. Now all these separate quantities here, we can't really measure them. But together, the cations and anions, we can measure that. So we can measure this gamma of the cations to the stoichiometric coefficient of the cations times the gamma of the anions times the stoichiometric coefficient of the anions. Remember, this is gamma nu, gamma nu. So what we're going to do is we're going to find another gamma. This will be our gamma combined plus or minus. Now this is what we're going to call our molality scale mean ionic activity coefficient. So basically that tells us we're working on a molality scale now, not in our mole fractions. And this ionic activity coefficient for the entire electrolyte, not just for the cations or anions separately. Now to calculate it, it goes like this. The gamma, the activity to this exponent. So we need to add both coefficients. Now these are both pluses, right? So this nu plus and nu minus, this is the, now I can't think of it. This is the stoichiometric coefficient of the cations. This is the stoichiometric coefficient of the anions. They're both positive. You just add them together and you get a higher positive number. They both have to be at least 1, obviously, so this is going to be at least 2. And likewise, you have the activity of the cations to the stoichiometric coefficient of the cation power, and then that is times the activity of the anions to the stoichiometric coefficient of the anion power. This could be 1 or more, any integer. This could be 1 or more, any integer. And this will work if you have just one electrolyte or if you have more than one electrolyte. Continue on physical chemistry, chapter 10, section 6. We're talking about ionic solutions still. So we showed before how the activity coefficient for the whole solute, plus and minus, is equal to, or to the nu plus nu minus power. That's equal to the gamma plus to the nu plus power times gamma minus to the nu minus power. So an example to make it clear would be barium chloride here. So 1 plus 2 is 3. So our gamma plus minus to the third power, that's equal to our gamma plus to the first, because our nu 1 is 1, times nu minus to the 2, because our nu minus here is 2. Solve for nu plus minus, then we get nu plus minus is equal to the gamma of the cation to the first power times the gamma of the anion to the second power, and all that to the 1/3 power. And of course, we only want one answer to that, the real root. Obviously, if you're a math major, you could find a couple of complex roots, but that won't tell you anything here. So then mu plus, or mu of the electrolyte here, is mu of the electrolyte in the standard state, plus RT times the natural log of our, what we just found here. Gamma plus minus to the nu, times the molality of the cations divided by the standard state to the nu plus, times the molality of the anions divided by the standard state to the nu minus power. Now remember, we define nu as just nu plus nu minus. So the molality of a substance I, that's the number of moles of substance I divided by the weight of A. So remember, A is our solute, or I is our solute, A is our solvent. And remember, to get the units correct, you need the mass in kilograms, not grams. Now, let's assume that we don't have any ion pairing. Then if we have our metal and our non-metal here, they're going to totally dissociate, and we get nu plus, the cations, plus nu minus, the anions. And then the molality of the cations is just going to be equal to the stoichiometric coefficient of the cations times the molality of our electrolyte. And likewise, the molality of the anions is just going to be equal to the stoichiometric coefficient of the anions times the molality of the electrolyte. So, and the M plus and the M minus, we're calling that the ionic molality, because it really is the molality of your ions in the solution. Continuing on physical chemistry, chapter 10. This is the last of section 6, actually. We're just finishing up electrolytes. So we showed before, so the molality of the cations to the nu plus power times the molality of the anions times to the nu minus power, that's going to be equal to, substituting in what we did before, nu plus times the molality of this electrolyte to the nu plus power, plus nu minus times the molality of the electrolyte to the nu minus power. Now we can separate those out. So we get nu plus to the nu plus times nu minus to the nu minus times the molality of I to the nu power. Because remember, nu is just nu plus nu minus. So that's how we were able to combine these two. Now, just like we did before for gamma plus then, we can do the same to have a nu plus minus. Not the same as this nu right here, obviously. This nu plus minus to the nu is equal to nu plus to the nu plus times nu minus to the nu minus. Now it's interesting, these both have to be integers. This one's not going to come out to be an integer. Now, an example, let's do magnesium chloride. So we're trying to find our nu plus minus. To the nu is just 3 because 1 plus 2 is 3. So we take 1 times to the 1 power and then 2 to the 2 power. So taking the cube root of that, we get nu plus minus is the cube root of 4. Again, we want only the real root. So then we get 1.587. So again, this is not an integer, obviously, but mathematically it works out, makes perfect sense. So now, substituting in that other equation we had up here somewhere, we get gamma plus minus to the nu times the molality of the cations divided by the molality of the standard state to the nu plus power times the molality of the anions divided by the molality of the standard state times the nu to the nu minus power. We can rewrite what we have here then, and we get gamma plus minus, or no, nu plus minus times gamma plus minus times the molality of the electrolyte divided by its standard state to the nu power. Now we can substitute the back in so we can find our chemical potential of our electrolyte. And that's just equal to the chemical potential of the electrolyte in the standard state plus nu times RT times the natural log of what we had here, our nu plus minus times gamma plus minus times the molality of I divided by the standard state. And this should be true for any strong electrolytes, because I think we're assuming no ion pairing. If we had ion pairing, then our nu is going to come out a little different, I think. This is Physical Chemistry, Chapter 10. We're starting Section 11 now, non-ideal gas mixtures. We're going to go through this pretty quickly just because we need it for later chapter. So, non-ideal gas mixtures. The fugacity, as F sub I, so we're talking about substance I, is the effective pressure in a mixture of gases. Now, the fugacity of the substance I divided by P naught, that's our activity, AI. So Fi has got units of pressure, because obviously P naught has units of pressure, AI is dimensionless. And then Fi, this is intensive. Well, pressure is always intensive, duh. And of course, you know, P naught is 1 bar for this type of equation. Now, for an ideal gas, we just have mu naught, or mu of substance I ideal is equal to mu I naught plus RT natural log of the pressure of I divided by P naught. Now, on the other hand, for a non-ideal gas, instead of having the pressure, we're going to substitute it in the fugacity. So the mu I for a real gas is equal to mu I naught plus RT natural log of the fugacity divided by P naught. So fugacity plays the same role as the partial pressure. Remember Dalton's law of partial pressures, but that you would have in an ideal gas mixture. But we're talking about a non-ideal gas now. Continuing physical chemistry, this is all we're doing for chapter 10. This is the end of section 11. So as pressure approaches 0 in a non-ideal gas, mixture of non-ideal gases, then the fugacity of each substance I approaches the pressure of substance I. So fugacity approaches partial pressure as the pressure goes down to 0. Now we're going to define this, I guess, as phi, as the fugacity coefficient. So this is going to be equal to the fugacity divided by the pressure. So it's going to be a ratio. And these both have units of pressure, so this will be dimensionless, obviously. So the fugacity is just going to be equal to this phi times the partial pressure of I. And remember, partial pressure of I, that's just based on the mole fraction of I times the pressure. This is always true for real, ideal, whatever. So that gives us, substituting in, gives the fugacity of I is just equal to this fugacity coefficient of I times the mole fraction of I times the total pressure. Remember, we're using X or chi for mole fraction and P for total pressure. So now we have the chemical potential of I graphed against the pressure, total pressure, remember. So we're starting at absolute 0 here. So notice an ideal gas mixture just sort of curves up here like this. Non-ideal gas, it's going to start out lower. The F is going to be less than pressure. The fugacity is going to be less than pressure. The reason is because the molecules, they're close enough together. No. They're far enough apart that the molecules won't get in each other's way. They won't be able to repel each other at all because of their volume. And then over here, the fugacity is going to be higher in the non-ideal gas mixture. And that's because as the pressure gets really high, the volume, the actual the volume of the molecules becomes important. So they'll actually repel each other because of the volume the molecules take up.